So before I start the talk, I want to tell you the story how I actually started working on this. And I would like to start maybe 7 years back in time, when I was an undergrad student, and maybe Ralph remembers. So I was sitting in Ralph's set theory or logic 2 lecture, and we were talking about Arensheim trees and Suslin trees, and I really liked that topic. The only problem was that afterwards you showed me measurable cardinals and projective determinacy and inner models. And so I started working on that because I fell in love with inner model theory, and I forgot about Suslin trees and Arensheim trees and all these kinds of things. And then this spring, Yair Hayut came to Vienna, and I was very happy that we found a way to combine both topics. So this talk will be about trees, combinatorial trees, and inner model theory. And the outline is the following. So I want to start with the tree side of it. So I want to just give you some background, what kind of trees we consider. And I will give you some rather easy upper bounds for the combinatorial property. Then I will give you a first lower bound as a warm-up. And this will motivate the notion of a seal tree. And then we will go more in the inner model theoretic direction. And the 2 main results is the first one, what happens in the context below a Woodin cardinal, and the second one, I will show that we can get a non-domestic mouse from the kappa perfect subtree property. And I will define what that is somewhere along the way. Okay, so all of this is joint work with Yair Hayut. So the first definition is very basic. We just say for any regular cardinal kappa, kappa or tree of height kappa is a normal kappa tree if each level has size less than kappa. I want to make sure that we have a split, say at least at each level. Then for limit ordinals, if we have a branch up to alpha, there's at most 1 least upper bound. And I want to make sure that whenever we take a node in the tree, for every alpha above, there is some stronger node T prime in the tree. Okay, and now we can already define the object we want to study. So let's look at the branch spectrum of a given regular cardinal kappa. We just look at normal kappa trees, and we check how many branches they have. So what is the cardinality of the set of cofinite branches of such trees? Maybe let me just give you some examples, and then you will see what I really mean. So the easiest case is just Aleph 0 or omega. In that case, there are exactly 2 possibilities. Either we have Aleph 0 many branches or continuum many. I mean, one thing is Koenig's lemma, the other thing is Cantor-Bendixson. And so for omega, this is not very interesting. For omega 1, this is actually something that has been extensively studied by Silver and other people. What I'm interested in is the case for larger cardinals kappa. So for example, I mean, if we just take some kappa bigger than omega 1, we can just look at the statement and ask whether kappa plus is in the branch spectrum. And for example, if there are no kappa Kurepa trees, then this is definitely the case. Kappa plus and even kappa double plus, whatever, will not be in the branch spectrum. Another property we can look at is we can just ask what is the minimum of the branch spectrum or whether kappa appears. So if the tree property holds, it means that every kappa tree actually has a cofinite branch, and we can also argue that actually the minimum of the branch spectrum is equal to kappa. Okay, let's think about some upper bounds. I will consider exactly the same properties as on the previous slide. Let's look again whether kappa plus is an element of the branch spectrum. Well, that's actually very easy to force. The only thing you need is an inaccessible cardinal. The second thing, I already said, it follows from the tree property. So what we need is a weakly compact cardinal. So far, so good. We are still very low in the large cardinal hierarchy. Let's see what happens if we take these 2 simple properties and just combine them. So what happens if we ask for both? We ask that kappa plus is not in the branch spectrum, and that the minimum of the branch spectrum is actually equal to kappa. And as usual, if you take 2 simple properties, you put them together, you get something very strong. So let me show you the upper bound. And this is the best upper bound we know at the moment. So let's take some cardinal kappa, which is less than mu supercompact, where mu is some strongly inaccessible cardinal above. Then we can collapse mu to be the successor of kappa. And this is going to give us a situation where this holds. So if we consider the Levi collapse of mu to kappa, and then we just add some subsets in the end, then in a forcing extension we can preserve the weak compactness of kappa, and at the same time get that the branch spectrum is actually just kappa or kappa double plus. And I mean, if you wonder where the strength comes from, it's actually, I mean, this is the really hard part. The hard part is preserving weak compactness, and therefore we need to start with a supercompact. But this is pretty standard. I mean, for people who know forcing, this is an exercise.
Is this a silver? Just keeping kappa super compact and making the weak compact?
Yes, I mean, we start with the supercompact. Yes, yes. I mean, it's really just this.
Forcing is a silver.
Yes. Okay, so the really interesting question for us is whether this is optimal. So what I want to study in this talk is whether we have lower bounds for this. So the first lower bound, 0 sharp. So if for some weakly compact cardinal, kappa, we do have that kappa plus is not in the branch spectrum, then 0 sharp exists, and this follows from the following fact, which is essentially due to Soloway. So if 0 sharp does not exist, then for every weakly compact cardinal kappa, we can actually construct a tree which has exactly kappa plus many branches. And I can also already spoil a little bit, so this tree will be constructed in L and we use covering. This is why 0 sharp is relevant there. And the interesting thing is, since we construct the tree in L, it actually has stronger properties than the one I'm aiming for here, because I mean, if the tree is in L, it's going to be very absolute. The one in L is actually going to be absolute to any outer model. I mean, let's look at a very related property or something very similar. Let's say we look at a tree and we ask that its set of branches is absolute to any set forcing extension, which doesn't do too much harm to kappa. So this is the following property. We start with a regular cardinal kappa, and I say a normal tree on kappa is strongly sealed if whenever we take a forcing extension in V, the set of branches does not change, as long as the forcing preserves that kappa is uncountable cofinality. So this is, in terms of forcing, the strongest thing that makes sense to state. And now we can ask whether we can actually get such a tree. Okay, I should be a little bit careful if I just say such a tree. This is very easy. So in Z of Z, we can just prove that there are strongly sealed trees with kappa many branches. I mean, this is a very easy example. We can just take a tree such that the number of ones is finite. Since the finite numbers are not changed by forcing, this is going to be very absolute. So this is a sealed tree, but it will only have kappa many branches. So the really interesting point here is whether we can get a strongly sealed tree which has kappa plus many branches. And this is even stronger than just asking that kappa plus is in the branch spectrum. This is asking that kappa plus is in the branch spectrum plus the tree witnessing that is strongly sealed. Okay, so this brings us to the actual construction. And if we are in the setting below a Woodin cardinal, we can actually construct such a tree. And let me first state the theorem. Okay, so let's suppose that there is no inner model with a Woodin cardinal. Then for every, in general, first for every regular cardinal kappa, we can actually construct a strongly sealed tree of height kappa, which has exactly kappa plus of k many branches. And then in particular, if we assume in addition that kappa plus is computed correctly, so kappa is weakly compact, then this strongly sealed tree will have kappa plus of v many branches. Okay, so how do we do this? I already mentioned that the original solar wave construction was a construction in L, and the most natural thing to do is to try to generalize that to the Jensen-Steele core model K. So let me give you a brief sketch of the argument. So we construct a kappa tree T in K, and we want to make sure that this tree, first of all, has at least kappa plus of K many branches. How do we do that? So the tree looks as follows. We look at some nodes. We maybe draw a picture. So in the end, all the elements in the tree are going to be generated like this. So we take some hull in K, or I want to do it a little bit more locally, so let's just say K up to kappa plus. And I throw in some ordinal row and some generating set X. And so these are going to generate the tree, and then I just transitive collapse it in order to get transitive models in the tree. And the idea is that if we have such a thing, we can also just look at, so let's call this thing our M bar. We can now look at the hull in M bar of, again, some rho bar and some, let's say, X prime. So taking hulls is a very iterative process. When we take the hull in this big model K, but if we have some intermediate model M, or M1 and M2, then taking the hull in K and collapsing it down to M0 is the same as taking the hull in M1 and collapsing it down to M0. And this is how the tree is going to look like. So the tree order is defined by one thing being the collapse of the other. So M0, X0 is less than or equal M1, X1 if there's some ordinal row such that M0 is not only the collapse of the hull in K, it's also the collapse of the hull in M1, the larger one, of rho and this ordinal, or this set X1, and this X1 collapses to X0. And of course, there's something to check. We need to check that this actually is a tree. It's a tree of height kappa, and it has at least kappa plus of K many branches. The key point is maybe to see that this is actually branching. Because if you take X to be the empty set, then what we get is just a line. We can take hulls and we can throw in ordinals, but there's not much branching going on. There's exactly one option. So the role of X is that we actually allow to split. If we take some X and some X prime, and none of them is definable from the other, and also not from the ordinals we throw in, then this is actually a proper branch, or proper split in the tree. And if we follow these X's along, each X is going to generate a branch through the kappa tree. And so if we start with 2 to the kappa many different X's, we get 2 to the kappa many, or kappa plus in K many different branches. So this gives us a giant tree. And the next thing to...
You have to worry that the levels are small, right? Because you don't want...
Yes, that's true, but if kappa is weakly compact, it's in particular inaccessible, and then it's okay. Yes. But this is a very good point. So you have to, I'm saying I want to have a kappa tree, so you have to make sure that the level is of size less than kappa.
You're only doing this in accessible.
Yes, and if kappa is a regular cardinal, it doesn't, actually we tried to do this and it doesn't seem to work.
By the way, this is Silver's construction for L.
Yes, this is very similar to Silver's construction for L.
It is.
But it's, this suffices, but the rest is different because to argue that this actually does what we want, you need to use more inner model theoretic arguments. But yes. So the next step we want to do is we want to argue that if we take a branch in V, it actually comes from something in K. So this tree, I mean, we constructed it in K, but maybe V sees more branches than K. K is very tiny, maybe. But we can argue using the fact that K is not so tiny, that this is not the case. So we actually have that in V, the size of the set of cofinite branches through the tree is kappa plus of K. And I mean, the very quick idea is that if we take a branch, we can look at the direct limit along the branch, and this gives us a model. Right? We always have a model and an element. This gives us some model, and this model is a mouse. And we can compare this mouse with K and use that K is universal and maximal to argue that in the end, actually, it will end up to be an initial segment of an iterate of K, and therefore it will already have all the subsets of kappa, and it will in particular have the branch. So once we have that, we are still not done. Because, I mean, there are two more things I'm claiming. The first thing, but I mean, the next two are easy. The first thing is that this tree is actually sealed. This just follows from forcing absoluteness of K. Whenever we take a set forcing extension of V, then K is not going to change. So the branches in the set forcing extension of V are still in our K. And the final thing is that we want to have kappa plus of V and not kappa plus of K. But we assumed that kappa is weakly compact, and this is actually where we use that it's weakly compact, exactly there. So the covering theorem holds, and kappa plus of K is equal to kappa plus of B. So this gives us a very nice tree, assuming that there's...
You said set forcing that keeps kappa of infallible cofinality?
Yes, in order to make sure that the tree makes sense.
At that point, because otherwise...
It was on... Yeah. It's part of the definition.
Yeah, okay.
And... okay, so this gives us a very nice tree in K. The first thing to ask is maybe, okay, what happens if we now maybe have a Woodin cardinal, right? I mean, this generalizes if we have that the universe is closed under sharps and M1 sharp does not exist. But what happens if, for example, there's a Woodin cardinal in V? Well, the answer is actually very easy. It's a short observation that we will not have a sealed tree with kappa plus many branches. And the reason is stationary tower forcing. So if we just suppose we have a Woodin cardinal above our kappa, we can take Woodin stationary tower with critical point kappa plus. This will preserve the tree and the large cardinal properties of kappa, but kappa plus will be moved. So if kappa plus changes, we have more branches in the end. So there's really no hope to ask for a strongly sealed tree in this context. So what do? We changed our definition. Asking for a strongly sealed tree was too much. We asked for a weakening, and this is motivated by the following lemma. So we go back to the tree side for a moment. So for any cardinal kappa, the following are equivalent. When we have a tree of height kappa, T has a perfect subtree, or every set forcing that adds a new subset to kappa actually adds a branch to T, or there's a kappa closed forcing that adds a branch to T. So instead of asking or a sealedness property where we say, okay, for any forcing, the set of branches stays the same, maybe we should restrict ourselves to special forcings, kappa closed ones, and then it's just the same as saying that we have a perfect subtree if we add a branch.
No isolated branch, or you want to split in points to big club also?
Perfect means that I can embed a copy of 2 to the kappa.
Embed?
Injective.
And monotone.
Yeah. I mean, I'm looking at trees, and if you want to, you can just assume that the trees are all on 2 to the kappa, maybe, by just some coding. And so let me just write what I just said as the definition. So if kappa is an uncountable cardinal, we say the perfect subtree property, short PSP. For kappa is the statement that every kappa tree with at least kappa plus many branches has a perfect subtree. So this is just like the perfect set property for kappa in this special case, or like the perfect set property for omega. It's exactly the same property. We just here have to say that we count the number of branches through our tree. So instead of asking for a strongly sealed tree, we can also just ask what is the consistent strength of this statement, which is clearly weaker than asking for a strongly sealed tree. And it turns out that the consistency strength is again very high. But first of all, the good news is the upper bound still works, actually by exactly the same proof. So again, let me just repeat. If we take a kappa which is less than mu super compact, where mu is strongly inaccessible, there's again a forcing extension, and the forcing is exactly the same. We Levi collapse mu to kappa, and then add a lot of subsets. And in this forcing extension, again, kappa remains weakly compact. The branch spectrum is exactly as before, and the perfect subtree property holds at kappa. So this is again very easy to see. But the interesting thing is now, okay, what happens with the lower bound? So the upper bound is still very high. We have our super compact and inaccessible above. The good thing is, I mean, previously the lower bound was a Woodin cardinal. If we ask for this, we actually go well past the Woodin cardinal. And what we can get is a non-domestic mouse. So I will say what that is in a second. Let me maybe first state the theorem a little bit more precisely. Okay, so let kappa be a weakly compact cardinal as before, and assume that the perfect set property holds at kappa. Or actually the same proof shows the following, or we can just assume that there is no kappa tree with exactly kappa plus many branches, aka that kappa plus is not in the branch spectrum. If one of these things hold, then there's a non-domestic mouse. And what does that mean? So if you prefer determinacy, it just means, or it implies that there is a model of ADR. For the large cardinal people, it means that there is a proper class of Woodin cardinals and strong cardinals. And yeah, I mean, I don't want to define non-domestic mouse because I think it doesn't make any difference. But what this means is basically that we can go very high up. It's far beyond a Woodin cardinal. And how do we prove this? So it's basically using the very famous stacking mice paper, which is Jensen, Schimmerling, Schindler, and Steele. Let me sketch the idea. So what we do is we again construct a tree. And now we construct the tree not on K, we construct the tree on S, where S is the stack of mice on KC up to kappa. So we assume that that all mice are domestic. And in this case, the Andretta, Niemann, Steele paper, which is called the domestic levels of KC are iterable, shows us that we can actually construct KC, and then the JSS paper tells us that we can actually construct the stack above that, and that the stack has a covering property, and this is the key thing we want to use. So this tree, T of S, has exactly kappa plus of V many branches, using the covering argument, which is due to Ralph Schindler, I think, from that paper, because kappa is weakly compact. Yes? No? Well, I mean, in the paper, you state that the stack, if kappa is weakly compact, satisfy covering. This is all I need. And it says that it's due to you, I think, in the paper. But okay, if no one complains, this is what we assume for now. Okay, but so this gives us that this is actually a tree which has kappa plus many branches, so we already get what we want from the second hypothesis. For the kappa perfect set property, we have to work a little bit more, because we need to show that this tree does not satisfy the perfect set property, or equivalently, we argue that the set of branches does not change if we add a Cohen subset to kappa. And the idea here is, I mean, this is using weak compactness again, and this is also using the fact that this forcing is extremely nice. So we basically have to argue that if we take the stack of mice and we go to a forcing extension where we add a subset of kappa, we do not add a new mouse, which changes the stack. And so this takes an argument, but once we have that, we can actually argue, since we don't add branches in this add kappa 1 generic extension, it suffices to get that we have the perfect subproperty by the folklore lemma I mentioned earlier. And therefore, the consistency strength of having the perfect subtree property at a weakly compact cardinal is definitely above this level of ADR, say. Okay, so let me summarize a little bit and maybe look to the future. So we have 3 different questions we looked at. I mean, we just looked at the question whether there is a tree which has exactly kappa plus many branches. We looked at the question whether we can get a seal tree with this property. And we looked at the question whether the kappa perfect subtree property holds, which basically means that we can get a tree which has kappa plus many branches, and the set of branches is not changed by just adding a Cohen subset to kappa. And for all of these properties, let's take the sealed one out, because this one we already saw that we cannot get it past the Woodin cardinal. For the other 2, the upper bound is at a supercompact with an inaccessible above, and the lower bound is at, say, a proper class of strong and Woodin cardinals. So there's still a huge gap in between. And so maybe the first question is whether we can actually push the lower bound a bit higher. I personally believe that we can, for example, get ADR plus theta regular, but it just takes a lot of work to sit down and push that argument through, because this would mean that we cannot use this nice stacking mice paper, but we really have to work through the Cornwall induction. When we checked the Cornwall induction up to ADL of R, and this worked perfectly nice. But so this is one way to go. But then eventually we will run out of techniques of inner model theory, and we have to wait for inner model theory to go up to supercompact in order to actually prove that we get where we want to. But looking at the arguments, it actually feels like this is the direction we should go. I believe that this is actually much stronger, and we should probably get very close to a supercompact with this property. And before I finish, let me just mention one quote I stumbled upon and which I liked, especially in the current times. So never say that there's nothing beautiful in the world anymore. There's always something to make you wonder in the shape of a tree and the trembling of a leaf. Thank you very much.
Thank you very much, Sandra. And because we are filming, the questions will be taken on the microphone. So, do you have any questions? That's fine. You can speak even if you're on a microphone. Yeah?
Just maybe I missed or forgot this already. Your summary that you gave was for kappa weakly compact.
Yes.
And what was it again about inaccessibles, not weakly compact? That I think you said at the beginning, and an upper bound for that.
If you just have an inaccessible, maybe let me just go back to the slide. There. So if you have an inaccessible, you can get that kappa plus is not in the branch spectrum by just Levi collapsing the inaccessible. But the problem is that you will lose the weak compactness of kappa. So, or if you want to phrase it otherwise, what you lose is the fact that the minimum of the branch spectrum is equal to kappa.
Oh, we could, yes, of course.
Because this follows from the tree property.
Yes.
Thanks. Bye.
There's an old result, an important result of Jensen's that kind of didn't make it into your story. Suppose V equals L. I know that's hard for you to suppose, but for a moment. Kappa carries a Cantor-Bendixson if and only if it's not ineffable, right?
Okay.
Right, the strengthening weak compactness. So, you can ask what happens with the perfect set property at ineffables. What happens is that it still is going to fail because, in L, because there are things called weak Cantor-Bendixsons. They're like Cantor-Bendixsons except they stationarily often are thin. That is, for stationarily many alpha, there are only alpha many nodes on level alpha. So clearly that can't embed 2 to the less than kappa, right? Can't embed the. So this gives you. These also give common self, and these exist everywhere now, ineffable or not.
Yes.
So I'm kind of thinking that maybe another thing to look at here is these weak Cantor-Bendixsons. only needs a certain degree of a certain amount of condensation. It could be these very large inner models. I don't know how large the inner models are today, but maybe they have these weak trees, and then you can play with those and get your lower bounds from them. You see what I mean?
Yeah. So I mean,
it's not just trees are not the only way of killing the perfect set property, even in LOE models.
Yes, but so I mean, for one thing, I mean, one would have to study the notion of condensation you actually need for that, because for the larger models, there's less and less condensation.
It's a pretty weak form of condensation.
And I mean, the other thing is, so in all of these arguments, the reason why we used recompactness, or what gave us the strength, is the fact that there's a covering theorem at that level, because talking about kappa plus in an inner model and kappa plus in V is a completely different thing.
And
so this is really what gives us the strength.
Is the absoluteness of the successor of a weak compactness.
Yes.
Right, I agree.
And I mean, so if you forget about recompactness and you just give me a regular cardinal such that the successor is computed correctly, I'm happy. Yeah. I mean, then the rest goes through. Yeah. Recompactness is really mainly used to get the covering theorem. Yes. But I mean, I don't know of any version of the covering theorem which would give you covering at a successor of a regular of this form.
I understand.
Thank you, Sai. Other questions? Maybe I'll have a question. So when we think about tree property, we look at situations when it can hold many cardinals at the same time, or a few cardinals, 2 or 3. So how about studying the branch spectrum at several cardinals at the same time?
Well, I have not looked at this. I mean, I think it's definitely an interesting question. The problem might be similar to what I just said to Sai. I mean, in this case, where we got the strength from is weak compactness. So if you want to look at several cardinals which are successors of each other, this will be a problem.
What if you collapse several large cardinals to become successors of each other?
Yeah, but we still need that they remain weakly compact.
Oh, okay, so then that won't work.
So, I mean, these methods, I think, will not be able to answer that question. But maybe, I mean, a related question is also, I mean, in this case, we get that, for example, kappa plus is missing from the branch spectrum. What happens if we ask about kappa double plus? All of a sudden, the methods of inner model theory are just completely out of the picture, because, I mean, inner models tell us a lot about computing kappa plus correctly. But if we change the cardinal, we are asking about this. Is wide open. So this is maybe another interesting question if someone wants to think about that.
Thank you very much, Sandra. Any other questions? No, well, thank you again.